And yeah, so I think we're gonna get started off with Ruben Van Belle talking about convergence of martingales via enriched dagger category. So take it away, Ruben.
Yeah, thank you. So hello everyone. Well, yeah, I'm going to talk about martingales. This is a joint work with Paolo Perrone. And in particular, I'm going to talk about the convergence of martingales. We're going to use some category theory to do that, namely these enriched dagger. So the plan is to first say something about martingales, what are martingales, what's intuition, and then we're going to do the category theory. So we're going to focus on a category called firm and a functor ln, and then we're going to look at all kinds of different structures and properties that these two things have. And from that, then we can get a martingale convergence result. Okay, so for martingales, we need conditional expectation. So I'll first tell you what conditional expectation is. So if we have a probability space, so a set with a sigma algebra A and a probability measure on that measurable space, and if you have a subset, a sigma subalgebra B of A, then we can look at a random variable on X that is A measurable, some integrable random variable. And then we say that the conditional expectation of that random variable F that is A measurable is a B measurable integral map now, which we use this notation for. So it's again a map from X to R that is B measurable now, such that integrating F or integrating the conditional expectation over subsets in our smaller sigma algebra is the same. So yeah, and the intuition sort of is when this B is a sub algebra of A, then your conditional expectation can take less different values. So you sort of integrate certain things, partially integrating certain things to get your conditional expectation. So an example of this, if we have a probability space, yeah, just this space, but the Lebesgue measure may be normalized. And we look at the sine function, that's definitely measurable. If we then look at this sub-sigma algebra with just these four subsets, then our F is, of course, this red function, and the conditional expectation is this blue function. So you see, we sort of, yeah, we have integrated under here and then normalized and here as well. And we can take less values because we only have four different measurable subsets. Okay, so that's conditional expectation. So we need to say something about martingales, or about to define martingales. So what's the martingale? So we start with a directed coset, usually natural numbers or maybe the real line, positive real line. And again, we fix a probability space. And now instead of one sigma subalgebra, we take a bunch of them. And that in an increasing way. So they're ordered. When I1 is smaller than I2, then BI1 is a subset of BI2. And yeah, all these data combined is called a filter probability space. And this is then called a filtration. So yeah, what's a martingale then? So we have a collection of random variables, Fi from X to R. They're all integrable. And Fi is measurable with respect to Bi. And then this is the martingale condition that if we have an Fj and we take the conditional expectation with respect to an earlier sigma subalgebra, then we get Fi. Yeah, so and then we can also talk about backwards filter probability based on backwards martingales if we have a decreasing net of sigma subalgebras. Okay, so what does that mean? So this is an example that Paolo made, which I think visualizes martingales very well. So if every picture is a random variable, sort of, then this is the conditional expectation of this. So you can sort of interpret that as like every 4 pixels, we take the average color and that becomes this bigger pixel. So yeah, the operation of conditional expectation in this example means pixelating the picture. And so since the sigma algebras increase, we always get more information and we can get more values or more different values. So we get a finer and finer picture. So we can refine the picture more and more as the sigma algebras increase. So then, ideally what we would like is that there's like an ultimate refinement such that all these pictures in the martingale are pixelated version of this one big refinement. And that's what the martingale convergence theorem says, that we can usually do that under the right conditions. So what are these conditions? So if we have a martingale, that's Ln bounded, and it's bigger than 2 on some filter probability space. Then there exists an f in Ln xa such that all these fi's are indeed a refinement of this f. And even more, the fi's converge in Ln. And then again, there's a similar theorem for backwards martingales. So yeah, and the interesting thing here is that we have sort of 2 sort of limits going on, where if we have this refinement, this common refinement, which is reminds us of a categorical limit maybe. That's common refinement, but then we also have this topological limit. So we want to have sort of categorical framework that covers these these kind of limits, and that's sort of the goal of our paper. Okay, let's then now talk about the category theory, maybe. So yeah, we're going to define this category current. So we have 2 probability spaces, X and Y. And then we say that a Markov kernel is measure preserving if this is satisfied. So in the case that your K is a deterministic Markov kernel, then this is really saying the push forward of P along your K is Q. Maybe another way of interpreting this is if we have a 1 that points to P in X and points to Y in Q, then that triangle commutes. That's what measure preserving means. And then we also have this almost surely equal definition for Markov kernels, and that is, well, they're almost surely equal for every P. And then the set on which it's actually equal depends on B as well, of course. Okay, then what is this category current? So the objects are essentially standard Borel probability spaces. So standard Borel space is when it's when it comes from a Polish space, a separable Polish space, and then probability space, and then this essentially means that it's a probability space that is isomorphic to such a standard Borel probability space. So those are the objects. Then the morphisms are equivalence classes of almost surely equal measure preserving Markov kernels. So we saw the Markov kernels, they have to preserve the measures because it's probability spaces. And then we take quotients or equivalence classes when of almost surely equal kernels. And then the composition is given by Markov kernel composition, and that is well defined. Then we're also going to use this category of Banach spaces. Banach space and one which is linear maps. I use this notation for that. Then I use the full subcategory of Hilbert spaces. The notation is that for. Okay, then this functor Ln. So an n number between bigger than 1 can possibly be infinite as well. And it goes from kern up to ban. And on objects, it's defined in the way you would expect, I guess, from the name of the functor. So it sends a probability space to the Ln space. So that's random variables on X that are have a finite nth moment, I guess, or have a finite Ln normal. Okay, then what about morphisms? So if we take a Markov kernel, so it's really an equivalence class of measure preserving Markov kernels, but I'm just going to say measure preserving kernels from X to Y. Then we want to define a linear map from Ln y to Ln x. So let's take a random variable in Ln y, and then we can define a random variable in Ln x in the following way. So it sends every x to this integral, and this is really Markov kernel composition, really, if we interpret this f as a deterministic Markov kernel. So we have turned our f into a random variable on x, so that gives us this operation. It's the one which is linear map, so that's a mapping. Okay, so that defines the functor. Then a remark: in the case that n is 2, then our L2 space is a Hilbert space, so then this factors through Hill. And I'm also going to, when I write L2, I'm just going to assume that the codomain is Hill. Okay, then we had all these different structures and properties that these categories have. And the first one is that it has a dagger structure. So I'll just remind you what the dagger category is. So a dagger category is a category C together with a functor from C up to C, such that it's the identity on objects. And if you apply the dagger twice, then you get the same thing. Okay, an example of this category of Hilbert spaces, then you can define a dagger structure by taking adjoints of your linear maps. Okay, then the dagger structure on this kernel, you have this current category. So if we have a measure preserving kernel, then there's this thing called the Bayesian inverse of K. So that is a measure preserving kernel in the other direction, such that for every A, we have this property. So what this really means is, for example, if K is deterministic, then every Y is being sent to the conditional probability on X given the pre-image of your element Y under K. So it's not obvious that such a thing always exists. But then there's this nice theorem that if you have standard Borel spaces, you can essentially standard Borel spaces, then such a Bayesian inverse always exists and is almost surely unique. So in particular, it's an actual unique morphism inferred. Okay, so that then gives a dagger structure by sending K to this Bayesian inverse. And to see that this satisfies the properties of a dagger structure, so you just write down the defining property of your Bayesian inverse. Since this holds for every A and every B, that means these have to be almost surely equal, and therefore you have equal in the curve. Okay. So yeah, we also have this L2 functor that goes from one dagger category to another dagger category. So then we might ask ourselves, does that preserve this dagger structure? And so yeah, it does. So you can write that as this commutative diagram. So first applying L2 and then taking the dagger is the same as taking the dagger and then applying L2. So concretely, what does that mean? So if we have a measure preserving kernel here, then this commutative diagram means that this is equal for every f and every g. And this is the inner product of our Ln space or L2 space. And then a particular example. So if we again take B as a subalgebra of A, then this map that is the identity on the sets is measurable and measure preserving, of course, because it's a subalgebra of A, and we can call that pi. And if we then look at G, an indicator function for some B in B, then this equality exactly means that this holds. And then if you remember the first slide I showed you, this is exactly the defining property of conditional expectation. So that means that precomposing this pi plus with f is exactly the conditional expectation of f with respect to b. Which of course, I tell you this because that's going to be important for the martingales later. Okay, so what do we have so far? We have these categories and these functors, and they have a dagger structure for current that's given by Bayesian inversion. In HILP, it's adjoints, and our functor L2 preserves the dagger structure. Okay, so let's continue with the other properties or other properties of the categories, namely the idempotents. What do they look like, and what can we say about those? Okay, so I'm first going to define a dagger idempotent. In our dagger category C, has to be an idempotent, and then the dagger is of the ease itself. And then if we have idempotents, so we can talk about splittings, and for dagger idempotents, we can talk about dagger splittings. So a dagger splitting of an idempotent like this is a pair of two maps such that this composition is the identity and the other composition is our idempotent, and then with the property, the additional property that they're each other's dagger. Okay, so that's definitions. Okay, let's look at the idempotents or the dagger idempotents in these categories. So if you have a Hilbert space X and a dagger idempotent E, then that has to be equal to the orthogonal projection on the image of this map. And then a dagger splitting is given by, well, the inclusion and the orthogonal projection. So we see if we compose these, then that's exactly this projection map. And if you compose them the other way around, then that's going to be like. And there's each of they are each of those actions as well. So it's a dagger splitting. So yeah, this image of E is always closed because it's an idempotent. So that means we have this isomorphism. So every dagger idempotent, we can send that to its image. That's going to be a closed subspace, and then every closed subspace gives us a projection map like this, an orthogonal projection, because we're working with Hilbert spaces. So for general Banach spaces, that doesn't work anymore. That gives us a dagger item, and it's a projection. Okay, then for our other category of Markov kernels. So I'm first going to give you an example of a dagger idempotent, and then we're going to say a bit more about it. Yeah, if all the idempotents can be written in that way. So if we have a standard Borel probability space and sigma subalgebra B, then yeah, we can look at this map again that I showed you before. So the identity set-wise, but then it's measurable with this B subalgebra. Then this is a dagger idempotent. Yeah, almost by construction. And yeah, Y plus was a conditional expectation operator, really. So if you pre-compose this with a random variable, then that's taking the conditional expectation. So we can interpret these EBs as sort of conditional expectation operator. So yeah, that gives us again a map for every sigma subalgebra. We get a dagger idempotent, namely this one. And then the proposition here is that this is rejected. So that's not obvious, but every dagger idempotent can be written in such a way. However, it's not necessarily injective. So we can make it injective to, well, just identify the subalgebras that are being sent to the same idempotent. So that gives us a equivalence relation. And then yeah, we can also say a bit more about these equivalence classes. So every equivalence class has a finest element, and that's the invariant sigma algebra. And we use this notation for that. Okay, and then an interesting property about these idempotents that yeah, these dagger idempotents is that there's an order on these sets of dagger idempotents. So we say that for two dagger idempotents, E1 and E2, we say that E1 is smaller than E2 if we have that E1, E2 is equal to E4. So and that defines a partial order. So okay, in the case of Hilbert spaces, if we have two dagger idempotents, a Hilbert space X, then well, those correspond to two closed subspaces, and then we see that this property, yeah, first projecting on A2 and then projecting on A1, if that is also equal to projecting on A1, then that means A1 has to be a subspace of A2. So we see that this idempotent order corresponds to just the inclusion of your subspaces. So yeah, that means we have an isomorphism of sets. Then for the other category kern, it's yeah, a bit more complicated. So if we have So you need to define something first. If you have probability space again, and we have two sigma subalgebras, then we say that B1 is almost surely coarser than B2 if for every B1 there is a B2 in B2 such that symmetric difference, so this symmetric difference has measure 0. So that means your measure cannot really tell the difference between B1 and B2. And then we rewrite this. So yeah, in particular, if B1 is an actual subalgebra of B2, then this is also definitely. So this is sort of the up to null set version of the usual inclusion. Okay, and then we have the following results. So this holds if and only if we have this sort of inclusion, order, and that's if and only if these invariant sigma algebras are actually inclusion. And that means that we get an isomorphism as follows. So, well, this was just defined on sigma subalgebras, but because of this result, we can also define it on equivalence clauses, and that's well defined. And then, yeah, because of this, we get exactly that in correspondence. Okay, so we have both sets of these dagger idempotents, so we can maybe also look at the suprema and the infima indexes and what they look like. And in particular, we're going to focus on directed suprema and infima. So first for our Hilbert spaces. So we have an Hilbert space X, and we have a co-filtered collection of dagger idempotents. Then that corresponds to a collection of closed subspaces ordered by the just inclusion. And then the supremum is the union closed. That's again a closed subspace of X. So that means that the supremum of our dagger idempotents is exactly this projection map on this scale. And yeah, similarly, we have something for the infima. Yeah, here, because the intersection is already closed, we don't have to do it. Anything else is just the intersection. But for the directed suprema and infima in Kern, it's a bit more complicated. So okay, fix again probability space, and we're going to look at a co-filtered collection of sigma subalgebras, but ordered by the inclusion. So that's in particular ordered by the idempotence order, but we're just going to look at the ones that are that come from an actual inclusion, and then we can say that the supremum is, well, the thing that you would hope it would be, right? So it corresponds to the supremum of your sigma subalgebras, namely the union, and then take the smallest sigma algebra that comes. So, and that works for all these co-filtered collections. However, for the infima, it's a bit more complicated. So for a decreasing sequence, we can still have our dual results, but for a general collection, we cannot just simply copy this. So then we have to take the union of these finer sigma algebras, so the finest one in the equivalence class, and then take the intersection of those. And you see then the thing that you might think it could be is actually smaller inside of the total. Yeah, so another characterization of these infima and suprema is as follows. So suppose we have a filled collection of dagger idempotents that all have dagger splitting like this. We have another one E with another dagger splitting. Then we can say that this E is the supremum of all these EIs, if and only if this diagram is a limiting diagram. And yeah, that's something that we're going to use now. But first, yeah, L2. Yeah, we can ask, does that preserve well, does preserve the order, but does it preserve these directed suprema and infima? That's maybe not always the case, but in our case, that is the case. And then combining that with the previous result, that means if L2 preserves the suprema, that corresponds to saying that L2 preserves the limit of these diagrams. And duly the co-limits and the infima. Okay, so we're going to apply that now. So if we have an increasing sequence of sigma subalgebras with a joint B, then yeah, we can write that as saying this diagram has these limits, where again these maps are always the identity on the sets, and then they're measurable because they're ordered in that way. Then by the two previous results combined, we can say that L2 preserves the limit of this diagram. So that means we have that this has to be the co-limit of all these L2 spaces. But we also knew that L2 was a dagger functor. So we can first apply the dagger functor, and then because L2 preserves the dagger structure, the asterisk and the plus switch, and we can say that this is the limit of this diagram. And remember, these were always sort of conditional expectation operators, right? Okay, so that allows us to say something about martingales, namely the first part of the martingale convergence theorem, that there's this sort of common refinement of all the elements in your martingale. And the proof is in the following way. So our L2 bounded martingale, we can represent that as a cone over the diagram here. And here it's important that it's L2 bounded because they have to be one Lipschitz. Okay, so we have a cone over the diagram. This is the limit of the diagram, so that means there's a unique F such that these are all refinements of this F, because these are conditional expectation operators. Okay, so that's the first part of our martingale convergence. Okay, in a similar way, we can do austerely, and then we have a backwards martingale convergence result. But then, because then we're working with this infima, we have to be a bit more careful if it's not a sequence, if it's a general co-filtered net of sigma subalgebras, that this B then might be this the infimum in the idempotent order. So maybe a bit bigger than what you maybe would expect. Okay, so what do we have so far? We had that, we sort of represented the idempotent in these categories. In Kern, that was equivalence classes of sigma subalgebras. In help, there was this closed subspaces, or that's known that there are these closed subspaces. The order was this sort of inclusion up to null sets kind of order, and in the Hilbert spaces case, it was just the actual inclusion. The direct suprema were the ones that you would expect, the ones that you would hope for. The infima for Hilbert spaces was also the one that you would expect, but then for in Kern, it was a bit more complicated. And L2 preserved all these structures, so it preserves the order and these kind of infima and supreme. Okay, So, and that gave us this, all this information gave us like a first part of the martingale convergence term. But now we want to also say something about the topological limit. So that's where we're going to need this enrichment. So we're going to enrich over topological spaces. So then we probably, we want our category of topological spaces to have a monodal closed structure, which you can define in the following way. If you have two topological spaces, you can define a tensor product by giving this, the Cartesian product of the sets the following topology, namely the topology generated by all these maps. So the final topology that makes all these maps continuous. And then as internal one, you can look at a split set of all continuous maps from X to Y, and you can give that topology of pointwise convergence. Okay, and that forms a monodal closed structure on top. Okay, then of course we want our the categories that we've been working with to be enriched over top. So for Banach spaces, if you have two Banach spaces X and Y, we can look at the sets of one Lipschitz linear maps from X to Y, and then we can define a topology on that, sort of variation of this strong operator topology. And that's defined in the following way. So if we have a net of one Lipschitz linear maps, we say that it converges to F if and only if it converges pointwise. Really, so for every X, we have that Fy X converges to Fx in Y. So in the Y space. Okay, and that then defines them. Yeah, that makes Ban enriched, and in a similar way, you can enrich help over top. Okay, then our other category, kern. So if you have again two probability spaces, essentially standard Borel probability spaces, then we define a topology in the following way. We say that a net of measure preserving kernels converges to a measure preserving kernel K if and only if this integral goes to 0. So there's sort of an L1 aspect to it and a pointwise aspect. So we want for every B that this K lambda B converges to KB in L1. And okay, that defines topology on our set of measure preserving kernels, and we call it a one-sided topology, and that enriches kern over top. Okay, so we have this topological space now of maps from X to X. We can then look at the subspace of idempotence. And what topological things we can say about that subspace. So it's a closed subspace, and the convergence of these dagger idempotence that we could represent like this converges to EB if and only if for every F we have this kind of points in L1. So you might maybe already recognize some like martingale convergence property here. Okay, so we have that all our categories are enriched over top in a certain way. Then we want our our functor L1 also to be enriched over top, which is the case, but there's even a stronger results, which is quite important because we're going to use that later. So if we have a net of Markov kernels that converges to certain Markov kernel, that implies that applying ln on the nets converges to ln of k, but it's also the other way around. So if ln k lambda converges to ln k, then the original kernels converge to k. So it's an if and only if statement, which is important later. Okay, so back to the overview. We had an enrichment. For Kern, it was with this one-sided topology. For Hill, it was this variation of this strong operator topology, really pointwise topology. For Van as well. And our L2 LN functors are also enriched. Okay, now we're going to define like a certain property that certain dagger categories can have. This idempotent Levy property. And it's really, based on this. So if, in R, if you have an increasing bound sequence, then that converges to its supreme. So in a enriched dagger category, in a topologically enriched dagger category, that translates to if you have an increasing net of dagger idempotents that has a supremum, then it also converges topologically to the supremum. That is the idempotent property. And then also the dual decreasing. So yeah, if it converges in order, then it converges in topology. That's the property that we're after. And then, okay, the category Hill has this property, and there's a bit of work to prove that it has this property, but it has that property. And if you know that this has this idempotent Levy property, then for Kern it becomes not too quite easy to prove that it also has this property. So to prove that, let's look at an increasing net of dagger idempotents times supremum. Then because our LN functor, L2 functor preserved the order structure and the supremum, we can say that these are also an increasing net that has a supremum. Then because in Hill we have this idempotent Levy property, that implies that it converges topologically. And then because of this results, if we have that these converge to this one, then we can go back. So these converge to these. So that means these converge to supremum as well. And then the decreasing one is this dual. So that means both these categories have this Levy property. Van doesn't have it. Well, we don't really need that here. So okay, so then the second part of the martingale convergence theorem is filter probability space, and we have a certain f in ln xb. So where b is the sigma algebra generated by the union of the bi's. Then we know that this converges to this in ln. So the proof for that is we already saw that the supremum of the EBIs is EB. We have this idempotent Levy property in Kern, so that means the idempotents converge topologically as well. And then because our L2 functor is, our ln functor is enriched, these converge to these, and because these are conditional expectation operators, that means for that this holds for every. Because this is the precomposition of this one with f, and because we defines the topology of these maps to be exactly this. Okay, and again, there's a backwards version where again we have to be careful with what this actually is. So this is the infimum in the idempotent order, and that's maybe just the intersection. Okay, so then the conclusion we have this martingale convergence theorem. So we already said that for an L2 bounded martingale, we can find a common refinement such that we can represent our martingale like this. And then by the previous slides, we know that martingales of this form converge topologically as well. So that gives us the second part here. Yeah, and then in our paper, we also have sort of a generalization to vector valued martingales. So that's by defining your LM function slightly different. But you can then sort of apply the same strategy to say something about those martingales. Yeah, that was everything that I had to know.
Right, let's take questions.
Sorry, can you say that again?
Yeah. Just
yeah, because otherwise it becomes a bit more complicated, and in the application we only really needed the actual inclusions and not this almost sure inclusion. But yeah, I guess you can generalize it, and then you get maybe an even stronger martingale convergence result. But yeah, the things here became a bit complicated, so we just stick with the actual inclusions.
Yeah, so you've worked out this nice categorical structure of this classical theorem, martingale convergence, this category of grounds and Banach spaces, river spaces. So now you have this nice abstraction. Do you have some new setting in mind that you could apply this to, or that this could generalize to, or something like that?
So yeah, well, we have these vector valued martingales. We've also sort of been thinking about maybe martingales that take values in a general G algebra or algebra of probability monads. So yeah, that could generalize martingales or general variables, and maybe we could use the same strategy to say something like that. But yeah, we haven't really worked out the details of that.
Do you have an idea what happened or something directed?
Not really, no. Yeah, but again, we focused on these directed because these filtered probability space, so they're filtered or co-filtered, the backwards version. Yeah, not sure about the other supreme.
And can you remind me, is there any
Yeah, sure. I'm not sure if there's a name. I don't know if you know if there's a known name for this.
Usually people say top is not your teaching close, but it's monoidal close, and this is the one of the structure that makes. I think they're not always going for this.
So you made it. You invented this.
No, this is not, but
That's what we're. Okay, thank you.
internal homes are fine for convergence.
How does this compare to like standard textbook proof of this cross-code convergence theorem? Like, are you saying is standard proof essentially saying the same things without saying it, or is this not better proof?
Well, the proof that I know is quite different. Yeah, it's different. Maybe there's I'm sure there's different proofs than what is a classical proof for me, but I think the proof that you usually see in textbooks is quite different from this.
So just About that, I mean, this seems similar to something involving like objective operators. Those shit like space, so we're not like, that guy component essentially a objective operator. But I haven't seen proof like that sort of proof before.
I see, I'm not completely aware of that, so so I know the
So
connection of
I think this might be.
If there are questions. All right, great. Let's thank our speaker again.